Okay, I hit start broadcast. It says I'm live on there. I'm not sharing the screen yet, though. Once I know that you can hear me, I'll try sharing the screen. So let me know that you can hear me. Okay, good, good, good. You can see me, nice. I'm trying now to share the screen instead. So tell me if you can see my screen. You might not see me very well because I've got my laptop tilted way back so I can write on it easier. Wow, okay, you can hear me. Can you see my screen yet? Once I know you can hear my screen or see my screen, then I'll start moving on. Awesome. Okay, I'm really glad. All right, so I'm going to try this again. Oh, fantastic. We're going to start over with problem 10.2 from practice problems 10.2C. The question was about problem 2I. It says identify the formulas of the organic products A to E found in the reactions below. And I had just started. And hop in on Twitter if you're going to ask some more questions after this, Mr. Thompson, ISB. I see a question from Sam. Sam, I'll get to you in a second. So question 2I for 10.2C. For the first reaction, we have an alcohol, a primary alcohol here, C3CH28OH. It's 9 carbons with an OH. We have an oxidizing agent here, and that oxidizing agent is going to cause this alcohol to become an aldehyde. So A will be an aldehyde. And then if I'm going to continue to oxidize the aldehyde until it gets to product B, it will be a carboxylic acid. Okay, so I'm going to go to the next page of my PowerPoint. The first product, A, is an aldehyde, 9 carbons. I know it's an aldehyde because I had a primary alcohol for my previous, for the starting reactant for reaction I, the first reaction, capital I had a primary alcohol. Primary alcohols will become an aldehyde. And yes, I should write all these hydrogens here, but I'm not going to just for the sake of time. The key here is recognizing that this is an oxidizing agent. And because it's an oxidizing agent, oh, I just lost my screen there. Because it's an oxidizing agent, it will take the alcohol and convert it into an aldehyde. I still have the oxidizing agent, and this is the most common oxidizing agent. Because I have an aldehyde, if I'm going to make the reaction continue under reflux, then I'll get product B, which would be a carboxylic acid. So 5, 6, 7, 8, 9 carbons, and now I have the carboxylic acid. That's product B. Product B would happen under reflux. Product A would happen under distillation. And so that's A and B. So from a primary alcohol, I can convert that into an aldehyde, or I can continue under reflux and convert that aldehyde into a carboxylic acid. Reaction 2 is, oops, I drew the wrong reactant. Reaction 2, I have a tertiary halogen. This is a bromine here, and I have sodium hydroxide, This is going to be a substitution reaction. We have not yet, sorry, I see a question from Leo on Twitter that relates to the previous question. How do you identify an oxidizing agent? For now, Leo, the most common oxidizing agent is going to be the oxidizing agent I mentioned in question A and B, K2CR2O7. You might see KMNO4. It's going to, and those are the two most common. And I would suggest for now, until we learn the mechanisms of those, I think that's all you need to know. I think if you know those two oxidizing agents, you'll be fine. When we draw those equations for oxidizing, we're not really drawing a balance equation. We're drawing what the main product is, and we're not worrying about the rest of the products. Okay, going on, continuing with question 2, I have a tertiary halogen with the bromine, and I have sodium hydroxide. The sodium hydroxide, remember, is going to be the ions. So this OH plus is going to replace the bromine. And I'm going to get as a product the tertiary alcohol. And that's my main product. And then I will also get NABR, which will be aqueous. Okay, I'm not writing that very well, sorry. So for reaction number 2, the product that is C is going to be a tertiary alcohol. It's a substitution reaction. I'm taking the hydroxide and I'm substituting it for the bromine. Reaction number 3, for that same question, I have a secondary alcohol. So I have a CH3 to a carbon and another CH3 with a hydrogen and an OH. This is a secondary alcohol. Secondary alcohols with an oxidizing agent. So the oxidizing agent is there. That secondary alcohol is going to become a ketone. So the ketone that it's going to make is 3 carbons with an OH. And there's my product. So primary alcohols, I'm going to go back for a second. Primary alcohols can be oxidized into an aldehyde and then a carboxylic acid. Secondary alcohols can be oxidized into a ketone. Tertiary alcohols will not be oxidized. Okay, so if I had a tertiary alcohol, oops, not H3, sorry, CH3. If I have a tertiary alcohol and I add an oxidizing agent and I have a catalyst, that's going to be a big no reaction. Tertiary alcohols cannot be oxidized. This second reaction made a tertiary alcohol. It made it by substituting the hydroxide for the bromine here. So that's making a tertiary alcohol. Tertiary alcohols cannot be oxidized. Secondary alcohols can be oxidized to form a ketone. So this product, this ketone, is D. And then the last reaction for this particular question is reaction 4. And it has an alkene, which in this case is ethene. And it has it reacting with bromine. We actually saw this reaction in class, not with ethene because it's a gas. We actually saw it with hex-1-ene. And we saw that the hex-1-ene reacted with the bromine and removed the color of the bromine. So the bromine is going to be added. This is an addition reaction. So the bromine is going to be added to that double bond. And the hydrogens are going to be still there. So that's product E. I particularly like, I particularly like that review question because it kind of gives you a little bit of everything, not quite everything, but a fair amount of everything that we did in organic. So that was from review sheet 10.2C, that was question 2I. Stefan wants to know, will we be tested on ozone? Well, I don't know how much I want to give away completely. I did tell you in block 7, so blocks 2 and 4, you're getting a little preview for tomorrow. I did not put a titration on the test. You can put that up on the Facebook group if you want to share it with people who are not able to join us. As for ozone, I would say ozone is something I could test you on. Ask me again later. Maybe I'll tell you. Oh, sorry. I just opened OneNote. Ask me again later and I'll tell you. I might tell you the real answer. Rahul asked, why does the tertiary alcohol not react with an oxidizing agent? Do you need to know it? Yes, you absolutely need to know that a tertiary alcohol will be no reaction. If I look at what's happening in the oxidizing of an alcohol, I'm going to use a different color here. When I'm oxidizing an alcohol, essentially I'm removing this hydrogen, because look at this carbon. This carbon doesn't have a hydrogen on it anymore. So I'm removing that carbon. If I go back to the primary alcohol, there were 2 hydrogens here. Notice that one of these hydrogens is now gone when it becomes an aldehyde. There's only 1 hydrogen here. So on the tertiary alcohol, there are no hydrogens here. No hydrogens on the carbon that can be removed to oxidize that carbon. So you absolutely definitely need to know that tertiary alcohols cannot be oxidized. Sam asked me to run through question 16. Yeah, so it looks like we're still kind of talking about this alcohol thing. Why, Rid, you just asked that question. Does it make sense now? You said, okay, thanks. Just make sure you tell me whether you want me to talk about it again or not. I think I got it, though. So I know there's a little bit of a delay between when you hear me and when you can respond on either Twitter or the chat. But I think we're okay on that one now. The primary alcohol makes an aldehyde because it's on the end. The aldehyde then becomes a carboxylic acid. If the carbon that has the alcohol group is in the middle, it can only make a ketone. And if it's tertiary, it can't make anything through oxidation. Sam asked me to go over question 16 from 10.2a. So, okay, I see from Rid that he wants me to talk a little bit more about this alcohol thing. I'm going to use smaller alcohols. I'm going to use 3 carbons. This is an OH. 3 carbons, this is an OH. And then I actually need to use 4 carbons for this. So I'm trying to explain what happens with a primary alcohol, a secondary alcohol, and a tertiary alcohol. So these are hydrogens. I'm not going to draw the rest of the hydrogens, but we definitely need to know that there are hydrogens on this carbon. So I'm talking now about this first carbon, the primary alcohol. This is the carbon that I'm sort of highlighting here. That's the carbon that will be oxidized in the presence of an oxidizing agent. And when it gets oxidized, it's going to lose this hydrogen, and it's going to form the aldehyde if I have it going under distillation. So notice that there used to be 2 hydrogens. Now there's only 1 hydrogen. Okay? If this is happening under distillation, I'll get the aldehyde and the aldehyde will come off. But if I do it under reflux, I can continue the reaction and I can actually form the carboxylic acid. But notice that the carbon that I've changed is the same carbon in every situation. It's this first carbon for a primary alcohol. And Leo, I see your question on exceptions. I'll get to that in a second. For secondary alcohol, this is the carbon that we're worried about now because that's where the alcohol is. So this hydrogen gets lost and it forms the ketone. Now, if you look at that middle carbon, this carbon that I'm highlighting now, there are no more hydrogens that can be removed. So that forms a ketone. and we're done. No more. If I look at the tertiary alcohol, this carbon that I'm highlighting now does not have any hydrogens attached to it directly. So I can't oxidize that carbon, even though it has an alcohol here. I can't oxidize that carbon because there are no hydrogens that I can remove. So that's the difference between primary, secondary, and tertiary alcohols in terms of oxidation. Okay. Leo, and Sam, I'll get to your question about 10.2a. Leo asked a question I can answer a little bit quicker, and it's about electron configurations. And he said, what exceptions do we need to know? The two that come to my mind, and I want to make sure that I'm looking at the periodic table now, chromium and copper. Chromium is going to be argon 4s1 3d5, and copper is argon 4s1 3d10. So those are exceptions you need to know. And I do want to go to Sam's question. Sam's question was question 16 from 10.2a. So I'd like to get to that. Question 16 from 10.2a. First question says, state and explain the trend in the boiling points of the first 6 alkanes involving straight chains. So when it says straight chains, no branching. So we're looking at those 6 alkanes: methane, ethane, propane, butane, pentane, hexane. Those are the 6 alkanes we're talking about. So it says state and explain. So as the carbon chain, and sorry, I didn't write that very well. As the carbon chain gets longer, boiling point will increase. There's your first mark. And the question is worth 2 marks. So 1 mark is to state the trend. So the trend is, as the carbon chain gets longer, the boiling point increases. So that's 1 mark. The second mark is to explain why. With larger molecules, we have increased intermolecular forces, which increases the boiling point. So that takes care of question I. State and explain the trend in the boiling points. The trend is, as the carbon chain gets longer, the boiling points are going to increase. This is because the larger molecules will have stronger intermolecular forces, which will increase the boiling point. And these intermolecular forces are going to be London forces because these are nonpolar molecules. They have larger molar masses, increased London forces, stronger intermolecular forces, which is a higher boiling point. The second part of that question, and Sam requested all of it, both parts. The second part of the question is the free radical mechanism for methane and chlorine. Rahul, so before I move to question 16II, Rahul asked if there will be titration. There will not be titration. There will be stoichiometry related questions, but it will not be a titration. I just didn't have enough marks for a titration. So Rahul, there is not a titration question. Sam, back to your question, 16II. Write an equation for the reaction between methane and chlorine to form chloromethane. And it's actually going to form HCl as well. That's 1 mark. So 1 mark comes from Leo. I'll get to that question at the end if that's okay. I want to finish this question. So 1 mark comes from just writing the overall equation. 1 mark is going to come from writing the initiation step. Initiation step 1, basically. And this is the Cl2 being hit with ultraviolet light to form 2 Cl radicals. That's 1 mark. Now I need to do propagation. Propagation will be worth 2 marks. And the first step in propagation, if I have the Cl radical hitting a methane, oops, sorry, not CH3, hitting a methane molecule, it will remove a hydrogen, and I will get CH3 radical plus HCl. And that is propagation, because I started with a radical and I still have a radical. This radical, CH3 radical, can collide with the Cl2 radical, and if it collides with enough energy in the right geometry, it will actually form CH3Cl, which is one of the products. These are both products. And in the process of doing that, it'll form another Cl radical. That Cl radical could start propagation over. So this is 2 marks. If I go back a slide, the question is worth 5 marks total. 1 mark is to write the equation, the overall equation, which I did here in the first step. The 1 mark is going to come from initiation. I've got to say ultraviolet light, or else I won't get that mark. 2 marks are going to come from propagation. There are other propagation steps that I could have, but these are the 2 main and most important propagation steps. And then 1 more mark is going to come from termination. And I can write a couple different reactions for termination. I'm only going to get 1 mark, but I can write a couple different reactions. And termination involves any time that 2 radicals collide. I'm going to get termination. I could write CH3. Let me try that one again. I could have a CH3 radical that collides with another CH3 radical. If it's the right geometry, it'll actually form ethane. And this is a side product. I'm only getting 1 mark for termination, but there are a couple different termination reactions. So let me just kind of summarize this question. The question is the free radical mechanism, and 1 mark just comes from stating the overall equation, which I'm circling right now. Methane plus chlorine, and let's see, methane plus chlorine is going to make the halogenoalkane, the chloromethane, and it's going to make HCl. This is a balanced equation. 1 mark is going to come from the first step, the initiation step, where I have the halogen, whether it's chlorine or bromine. It's got to have ultraviolet light here, and it's going to form the radicals. So this is a free radical. Remember that free radicals are very reactive. So that leads us to propagation. If a free radical happens to collide with the halogen or with the alkane, the regular alkane, it's going to pull a hydrogen from here and make HCl. It's also going to leave behind a radical. And so let me try and draw that for you. If I have CH4 and I have a Cl radical, it's going to form HCl, but it's going to leave behind a radical. Notice that this is a balanced equation. This step 1 is a balanced equation. I have 1 chlorine here, I have 1 chlorine here, I have 1 carbon, 1 carbon. 4 hydrogens, 3 plus 1 makes 4 hydrogens. So that's balanced. You're welcome, Sam. I'm happy to help. So initiation requires the ultraviolet light. I've got propagation where I start with the radical and I finish with the radical, and then I have termination where 2 radicals come together. If I have chlorine around and ultraviolet light is still happening, this chlorine can be broken down by initiation and continue the reaction. So until all of the chlorine has been attached to an alkane, or until the ultraviolet light gets turned off, this propagation will continue to happen, and initiation will continue to happen here, and termination will continue to happen, because these chlorines will continue to react. Okay? Now, Leo asked a question, so let me switch back to a pen here. Leo asked a question about the difference between London forces and van der Waals forces. And the IB changed the definition on this one. I want to make sure that I don't answer incorrectly. So give me a second. But my recollection, Leo, is that van der Waals forces is a more general term, and London forces is more specific. I'm going to go to topic 4. There's a PowerPoint on intermolecular forces there. And I'm just going to double check here. It used to be the case that van der Waals forces and London forces were basically the same thing. And in the new syllabus, that's not necessarily the case. So the term London dispersion forces refers to instantaneous induced dipole forces that exist between any atoms or groups of atoms and should be used for nonpolar entities. So there we go. London forces are for nonpolar entities. And if I have a nonpolar molecule like bromine, and I have another nonpolar molecule like bromine, those electrons are kind of around the bromines, but at any one time, you might end up with more electrons on one side, and that's going to push the electrons here away. So we have a temporary dipole inducing a dipole in this molecule, and that causes those London forces. It might be worth kind of going back to that PowerPoint and that video. There's some diagrams that might be helpful. Van der Waals is an inclusive force. So van der Waals includes London forces, and it includes dipole-dipole forces. But it does not include hydrogen bonding. So if we think about these intermolecular forces, London forces are generally the weakest, hydrogen bonding is generally the strongest. And that leads to, or can lead to, some discussions about boiling points. Sorry, stronger intermolecular forces lead to higher boiling points, all other things being equal. Okay? So Leo, I hope that answers your question. Ethanol and ethanoic acid can be distinguished by their melting points. State and explain which of the two compounds will have a higher melting point. I got that question from Rid. Ethanoic acid and ethanol. This is a great question because it really ties in a whole bunch of different units. Drawing Lewis structures, alcohols and carboxylic acids for organic and intermolecular forces. So this is an OH. This is ethanol. Oops, sorry. There we go. So the question was, ethanol and ethanoic acid can be distinguished by their melting points. State and explain which of the two compounds will have a higher melting point. And Pauline, I see your question. I'll get to you in just a second. The higher boiling point or higher melting point is going to be ethanoic acid. It will have a higher melting point because it's going to have, they both have hydrogen bonding. And so that makes this question a bit challenging. They both can hydrogen bond. Ethanoic acid actually has a slightly higher molar mass because of this oxygen, and that's going to increase the boiling point a little bit. But the other thing that's going to increase the boiling point is this carbon. So let me switch to the laser pointer. This carbon is going to be even more polarized because I have an oxygen bond here. Oxygen is very electronegative, so these electrons are going to be pulled towards this oxygen. These electrons are going to be pulled towards this oxygen. So this molecule will kind of be even more polar than this molecule. This molecule is polar here, and it can hydrogen bond. But this molecule has a carbon that has two oxygens attached to it, and it can hydrogen bond. So not only is it heavier, a larger molar mass, but it actually has a more polarized carbon here that's going to make the polarity stronger, which is going to increase the boiling point and the melting point. Pauline says, what is the overall charge on the complex ion formed by iron 3 and 6 Cn minus ligands? So We have iron 3+, and we have 6 cyanide ligands. So the formula in brackets is going to look like that, and it's going to be 3-. Pauline, the way that I know that that's 3- is the Fe3+ is 3+, iron 3, the Roman numeral 3 means it has a 3+ charge, and Cn- has a -1 charge, or 1-. So I have 3+, plus I have 6 minuses. So that's an overall charge of 3-. So I put it into brackets, and I end up with the overall charge. So Pauline, I hope that answers your question there. For the complex ions, look for the ligand. So these are ligands. Look for the ligand and the charge on the ligand. If we know the charge on the metal, we can figure out the overall charge. Let me give you a different scenario. This is an example of a complex ion. So Pauline, you didn't ask this question specifically, but this is maybe a related question. This is a complex ion. We know the overall charge. What is the charge on copper? How do we figure it out? Well, it's kind of like an algebra problem. I know the overall charge is 2-. So 2- has to equal the charge on copper plus 4 times the charge on chlorine. And chlorine, when it is a ligand, is going to be chloride. Woo, sorry. That was crazy. I hit the start button that took me to my desktop. Chlorine, when it's a ligand, is chloride. So it has a minus charge. So 2- equals copper plus 4 times 1-. So 2- equals copper minus 4. I have to add plus 4 to both sides. Copper equals plus 2, or 2+. Copper is 2+. This is 4-. That adds up to a total of 2-. Okay, so Pauline, I hope that answers your question sort of in multiple ways, not only helping you with the charge on the overall complex, but if you're given an overall complex, can you find the charge or the oxidation state of that metal? Let me know if there are more questions. I'm trying to think about what might be worth reviewing. I know that blocks 2 and 4, of course, we still have a review going tomorrow, and I'll be using your feedback on the Google form to handle that. So find me on Twitter, Mr. Thompson ISB, or send Rid a message, and he'll give me a question because I'm in a chat with Rid. Next question. Big picture here, in terms of this is something I can talk about while I'm waiting for a question. So I have something that I think I can talk about that might be worthwhile. You have 2 hours for your test. You have 79 marks. 35 are going to come from paper 1. 44 are going to come from paper 2. It is certainly the case that this test, you will, I emphasize will, be able to use your calculator and a periodic table, the full periodic table, and your data booklet for paper 1. It's not till next year that I take those away. Rahul, I see your question. I'll get to you in just a minute since I've started this little conversation here. So you want to think about how to manage your test. You have 120 minutes. And I would suggest that your paper 1 should take no more than 50 minutes. And ideally, your paper 1, if you go like 1.5 minutes per mark, that's 52.5 minutes. But you should really plan for no more than 50 minutes for your paper 1 question. If you get a paper 1 question you don't know how to do, skip it, come back to it. It's only 1 mark. Paper 2 involves more marks overall, 44. And so that will leave you 70 minutes for those 44 marks. And 44 marks is 66 minutes. Some of those marks are going to be easy. Some of those marks are going to be hard. You want to try and leave yourself as many minutes as you can for that paper 2. And when we start taking our real IB exams and mock exams next year, we'll talk about this in a different way, because paper 1 and paper 2 will be separate. But right now they're together. Your final, they're together. So try not to spend too much time on paper 1. Try to go to paper 2. And when you're working on those paper 2 questions, look at the marks. How many marks is it? Essentially 1 detail per mark. Leo, do you get info on polyatomic ions? Yes, for this year. Next year, you'll have to have some of them memorized. It's about 6 or 7. I'm going to be giving you the periodic table that has the polyatomic ions on the back. Okay. I want to get to Rahul's question. It says, could you explain the factors that affect the colors of complex ions? So if I want to talk about the colors of complex ions, essentially what happens is the presence of the ligand splits the d orbitals. So if I look at the d orbitals, normally I have 5 d orbitals, and normally they're all the same. And so let's see, let's use copper 2+. Copper 2+ is going to be argon 3d9. So there's copper 2+. But when there's a ligand around, the d orbitals will split into 2 levels. And these have different energy. This is increasing energy. So these electrons are here. And Rita, I see your question. I'll do that one next. This, I'll use a different color. This electron can receive light, and when it absorbs light, it's going to move up to this energy level. So it's going to absorb light, and it's going to absorb light. The complementary color from the color wheel that is in your data booklet is what you are going to, the complementary color is what you're going to observe, okay? So at the risk of screwing up here, I'm going to try it anyway. I'm going to try to show you the data booklet, and let's see if I can make it work here. I should still be sharing my screen. So shout out at me on Twitter or RID if you can see the data booklet now, because I want to show you a table. Okay, so I got to get there. Give me a second. Moving slow. These are common ions for the transition metals. That's a good table to know. The spectrochemical series. The spectrochemical series, I'm going to try to write on here. These are stronger ligands. It doesn't write very well with this particular app, so you got to forgive me. These are stronger ligands. So as I move this way, the splitting of those d orbitals will be larger, and the absorbing of light will be at a higher frequency. Okay, so now I want to go to this page where I have the color wheel. So if violet light between 400, let me find a better, there we go. Violet light, if the light is absorbed, is somewhere between 400 and 425 or so, it'll absorb violet light, and it will appear yellow. If it absorbs yellow light, it'll appear violet. If it absorbs light somewhere here between 650 and 700, it will appear, that's crazy, it will appear green. This particular app that I'm using doesn't, it's hard to write on. So you got to be able to use this color wheel, Rahul, to answer your question there in terms of the colors of those complex ions. I'm going to go back to that. So I've answered Rahul's question. I've answered Leo's question about polyatomic ions. Reid asked a question about chapter 616 test, question 15II. And I can do that. This is going to take a little bit of patience so that I can see that question. I don't have all the questions memorized, I'm sorry to say. Chapter 616, question 15II. I'm getting there. It's kind of slow scrolling here. 15II. Okay, I'm going to copy that. Take that to the PowerPoint. So I'm answering a question from the test. This is the 616 test. This is question 15. Ooh, sorry. This is question 15II. To outline one other way in which the rate of reaction can be studied in a school laboratory, sketch a graph to illustrate how the selected variable would change with time. We actually did a lab where I showed you 4 methods. And I showed you those 4 methods sort of specifically on purpose to show you different methods for following the rate of reaction. So let's think about what those 4 methods were. One of them is from question 15I. Sorry. One of those methods is from 15I. And that first method is the volume of a gas over time. And we collect the gas over time. We take the tangent. The slope of the tangent is the rate. But that was what the question was about originally. So now it says outline one other way in which the rate of reaction can be studied. So if you think about that lab, another way we did it was mass loss. So this is mass in grams. This is time. And it'll look like this. It may not ever go to 0. If I really want to draw a better axis, it's never going to go to 0. This would be for a reaction that bubbles, that produces gas. And the gas that we should produce is CO2. Probably not a very good method for using for hydrogen, because hydrogen is so light, the mass loss won't be very high. So Sam, the question is not what independent variables. Sam's question was, for this question, why wouldn't change in the temperature work? Temperature has an effect on the rate constant. True, but the question is not asking what changes the rate of reaction. It's asking how can it be studied. It's not asking what variable could we use. And it says outline one other way. And if you could think about question 15I, we were using volume to study rate of reaction. So what other ways can we study rate of reaction? We could study it with mass loss. We can study it using pH over time. Okay, and we did this. We actually had an acid that we were reacting with the base, which went up over time, and then at some point it kind of leveled off. We did this with absorbance over time. It might be the case that a product is being formed and we're tracking the absorbance over time. It might be the case that we are looking at absorbance and a reactant that's being used up. And we could study that over time. So this particular question, if I'm going to go back a few slides now, that particular question is how could we study rate of reaction, not what variables can affect rate of reaction. And so admittedly, I think it's not a very well worded question, but it didn't ask for variables. None of these methods are the variable being changed. They're the way that we measure the rate of reaction. And in all cases, we're having to find a tangent, where the slope of the tangent is the rate of reaction. So I hope that helps a little bit there with that question. I got another question from Rid. How surface area can change a VT graph? Okay. So this is volume, and this is time, and this is our initial rate of reaction. And let's say, let's make a reaction. This is calcium carbonate, which is a solid, and it is going to react with hydrochloric acid, and it's going to produce calcium chloride plus water plus CO2, and that CO2 is a gas. So we're going to collect that CO2. This is volume maybe in milliliters or centimeters cubed or something like that. Let's say that I have calcium carbonate and I have solid pieces, and I have 5 grams, and I have excess hydrochloric acid. So I'm going to do another reaction. I'll use a different color. I'm going to do another reaction where I have 5 grams of calcium carbonate. Actually, you know what? I'm going to mix it up a little bit. I have 4 grams of calcium carbonate, but now it's a powder. Because it's a powder instead of solid pieces, in this case, it has more surface area. So more surface area is going to react faster. So my initial reaction rate here is going to be a faster initial rate because I have more surface area. However, at some point, and I didn't draw this very well. Let me see if I can draw it a little bit better. It's going to be faster initially, but I'm going to finish with less CO2 because I only used 4 grams instead of 5. So the key here, like this might be a 2-mark question, draw the line for 4 grams of calcium carbonate powder. Those 4 grams of calcium carbonate powder are going to have more surface area. So it's going to be a little bit steeper here. But it's not going to produce as much carbon dioxide because the calcium carbonate is the limiting reagent, and therefore it will make less CO2. So that is that was question 15II on the test. I just got a question from Rahul. Rid, I see your question about K and T, and I'll get to that. But since Rahul asked about question 15, let's just look at the whole question. Give me a second here. I'm going to go back to that test. So this is the original graph. Okay, so this is 15I, if I remember my numbers correctly. This is 15I from that test. The question said half the concentration but double the volume. What's the curve going to look like? Half the concentration is going to be a slower reaction, but double the volume means the moles are the same. Moles equals concentration times volume. If I have half the concentration times twice the volume, the moles are going to be the same. Because I have the same moles, I'm going to finish at the same spot. However, because I have half the concentration, it's going to be a slower initial rate. So that's 15I. Now, I don't remember what I was. I'm sorry that I have to go back to it. Oh, no, that was 15. That was 15II. 15I, explain the shape of the curve. That's worth 3 marks. So if we're explaining the shape of that curve, the original curve now, when I'm explaining the shape of this curve, I want to talk about why is it so steep at the beginning, why does it get less steep over time, and why does it stop? At some point, the volume doesn't change anymore. So it's steep initially because there's a high concentration of hydrochloric acid, and the slope is equal to the rate. So I'm measuring the slope here. Over time, the hydrochloric acid gets used up, so the slope is now less. So the reaction is slower because the concentration of HCl is less. Then I'm going to run out of the limiting reagent, and I don't remember from the question what the limiting reagent was. But once I run out of limiting reagent, no more carbon dioxide will be produced. So I hope I've hit all of question 15, Rahul, for you there. Moving on, Rid asked, oops, sorry, I forgot to change to a pen. Rid asked, why does K increase with T, as T increases? Why does K increase as T increases? So let's take a generic reaction. So I have A becoming B, some generic reaction. The rate is going to be K, the rate constant, times the concentration of A. Let's assume it's first order. The temperature, if I increase the temperature, I will increase the rate. And I think that this statement is something that we can all agree on. If I increase the temperature, I'm going to increase the rate. And notice that this is at the same concentration. So if I increase the temperature, it's going to increase the rate. Number one, it's going to increase in the temperature will cause the particles to move faster and have more kinetic energy. Number two, that will lead to a higher frequency of collisions, which is going to increase the rate. Number three, because the particles have more kinetic energy, they will have a higher percentage of successful collisions. Therefore, because more particles will have an energy greater than the activation energy. So the energy of the particles is greater than the activation energy. So really, to answer your question, increase in the temperature, increase K. Well, if I'm looking at this equation and the concentration of A is staying the same, if I increase the temperature, I increase the rate. If the rate is going to increase, then K has to increase. So over time, sorry, not over time. So if I keep the concentration of A the same, but I raise the temperature, if the rate's going to go up, based on this mathematical relationship, K will have to increase. And K on some level is a measure of how frequently the particles are colliding and how frequently they're being successful in their collisions. So Rid, I hope that helps answer the question, why does K increase as temperature increases? I'm going to pause and take a drink of water here. Let me know if you have more questions. All right, I'm back. I just put some ice in my water. I'm waiting for more questions to come through on Twitter or through Rid. Rid has a direct line to me through a chat because he helped me get the Google Hangout set up here. So I am ready for more questions. And it's about, just to give you an update, it's about 3:04 p.m. I certainly can give you another half hour or so. And I've got some lab reports sitting at home waiting to be marked. I've got some planning to do for tomorrow for 3 different individual review sessions. So I'll give you another about half hour or so. I'm happy to answer more questions. What else do you want to know about? If you ever watched Kramer, this is Fraser Crane and I'm listening. Well, this is Mr. T and I'm listening. I'm ready for your questions. This is like the pregnant pause when the teacher waits for more questions. Last call for more questions. I know Leo is online or was. I know Rahul, I know Pauline, I know Sam, I know Rid have all been online. Any more questions? Kat wants 6II from the mock paper 2. Okay, from the June 2011 or May 2011. I think it'd be May. Give me a second, and I will look for that. So I'm going to write on my slide here just for a second. Mock paper 2, question 6II. This is May 2011. I put those, there's a link on the resources section of Haiku telling you, giving you a link to a folder that has these 2 practice papers in it. So let me find it. Rid, can you ask Kat 6A, 6B? Oh, maybe it must be, no, it could be B or F. Those are the only 2 that go to II. So I want to know, I guess I'm asking whether she wants 6B II or 6F. I guess I could do both. So until I hear from you, I'll do that. Why not? They're both relevant questions. The first question, 6B II. Excuse me. Why is silicon dioxide a solid while carbon dioxide is a gas at room temperature? And that question can be explained using bonding and intermolecular forces. SiO2 is a giant macromolecular compound. CO2 is just a molecular compound, and it's nonpolar. So the intermolecular forces are relatively weak London forces. Whereas here, it's this giant network. Every silicon is bonded to 4 oxygens. And every oxygen is bonded to 2 silicons. And it's this giant molecule. So if I'm going to melt silicon dioxide, I've got to break covalent bonds in this giant macromolecular compound. But if I'm going to melt or turn into a gas, carbon dioxide, I only have to break the intermolecular forces, which are relatively weak. So that explains the difference in why silicon dioxide is a solid and carbon dioxide is a gas at room temperature. The next question that actually had an II was question FII. Samples of sodium oxide and sulfur trioxide are added to separate beakers of water. Deduce the equation for each reaction and predict the electrical conductivity of each of the solutions formed. Sodium oxide is going to form sodium hydroxide. So let's see. Na2O plus water is going to form NaOH, and I'm going to need 2 of those. That's a balance equation. So in terms of conductivity, remember that sodium is going to form ions, sodium plus and hydroxide up. So this is going to be 4 ions, essentially, or 4 moles of ions. For the SO3, when I add SO3 to water, I'm going to get H2SO4. And H2SO4 is going to make H plus HSO4 minus. And this HSO4 minus is going to make H plus SO4 2 minus. So if I think about the number of ions that are present, I have essentially 2 times the H plus, and I have a lot of SO4. I'm not going to have a whole lot of this HSO4. And whatever HSO4 I do have will mean that I don't really have a full H plus. So this is maybe a little, I don't know if I'm explaining this very well, but there are less ions here. So I would expect this to have a lower conductivity. Probably, it is probably the case that this reaction is not maybe fully understood until we do acids and bases. And that's one of the, when I wrote the final, I really tried to make sure my questions were only questions that we have covered, whereas the sample paper you're getting here that Kat is asking about really covers everything. So some of the questions on those practice papers are not perfect questions for us because we haven't covered everything yet. But I think we have covered topic 3, which asks us to know these equations. And so I think that part of the question is certainly reasonable. More questions. I'm ready for you. Let me know if you've got a question through Twitter, or if you're online with a Facebook chat with Rid or something. Rid can ask a question of me as well. So Rid, I hope that answered Kat's question. So I just got a question from Rid through Kat, or from Kat through Rid. Why are some of the atoms in C60 fullerene are sp3 hybridized? So give me a second. I'm looking at something here. Oh, I'm looking at the mark scheme for that question, FII, and it says both solutions will conduct. I was thinking they were trying to be kind of tricky on us. They certainly would both conduct. This is a strong base. This is a strong acid. So they're both going to conduct. That's absolutely right. Rahul just asked a question. I'll come back to Kat's question. Rahul said, I can't find copies of our class tests on Haiku. I'd really like to redo some tests for practice. Yeah, I don't post blank copies of tests. I just post the mark schemes, Rahul. So you're welcome to write, cover the answers that you've already given. or anything like that, but I generally don't post my own tests as blank tests. There certainly are practice questions in the book that you could do that are sort of blank and without answers right there. There are, it's not fully legal necessarily, but there are some places where you can find past papers as well. I love giving you answers, but I generally don't post blank tests. I have posted, however, the formative quizzes. They serve a different purpose. So, Rahul, the formative quizzes are there if you want. So now I'm going to try and go to Kat's question that Rid sent me, which is, why are some atoms in C60 sp3 hybridized? And I would admit to being a little concerned about the question. I don't know that I would say that they are sp3 hybridized. If you were to ask me what their hybridization is, I would say sp2. Maybe there's something that I don't know. Kat, can you ask Kat? Sorry, Rid, can you ask Kat, or if Kat's listening, tell Rid where this information is coming from. Was it part of my PowerPoint, my review PowerPoint? Which I'm going to look at right now. I know there was a short section on the allotropes of carbon, which I'm looking at right now. I have to scroll through the 55 pages of syllabus statements. So, Rid, to answer Kat's question, or Kat, if you're able to listen, actually, it seems like it would be silly if you're not listening. Sorry, what am I saying? You are listening. You're just sending me questions through Rid. When I look at page 169 from your textbook, it says for fullerene, each carbon is sp2 hybridized and bonded in a sphere of 60 carbon atoms consisting of 12 pentagons and 20 hexagons. Structure is a closed spherical cage in which each carbon is bonded to 3 others. Can you tell me the mark scheme? Under bond angles, is this the mark scheme for the practice paper that you were working on? Also allow C60, sp2, and sp3. Is this from the practice paper? I'm scanning through the practice paper now. Describe 3 features. So is this, I'm assuming this might be from question 6. Let me go to the mark scheme. Question 6A. Yeah, I'm looking at it. For C60 fullerene, yeah, I have no idea why it says allow that. All of the literature that I've seen suggests that the carbon is sp2 in graphite, in graphene, and in fullerene. The literature I've seen is clear that in diamond, it's sp3. I think, I don't have a good answer. I think if I were to think about it a little bit, if you think about the structure of fullerene, there are some pentagons and there are some hexagons. So those bond angles are not all going to be 120 in fullerene. So I think that that structure may be why there are differences in bond angles between 109 and 120. Why they say allow sp2 and sp3, I'm not sure. I don't have a good answer for you. I would not have called it sp3. So I know that's not a perfect answer for you, Kat. Sometimes IB allows answers that are not perfect based on maybe, or maybe they allow answers that are a little bit more expansive based on what the scientists know, and maybe a textbook says they're sp2, but they're really some sp3 atoms there, and we're just not describing it that way. I do know for a course like this, even though you are studying college level chemistry, you are essentially covering almost an entire full year of freshman chemistry plus some sophomore level organic chemistry in our course together. It is college level chemistry, but even in college level chemistry, there are models and assumptions made that are not necessarily incorrect, but not completely correct. This might be one of those cases. I don't have a great answer otherwise. I know that maybe not perfect, Kat, but best I can do right now. So I am ready for more questions. That's from Jeopardy, by the way. If you ever watch Jeopardy, it's a great trivia show. I never did well on the literature or history or social sciences questions. I always did well on the science questions, the math questions, the music. It depended on music. Some music I know, some music I don't. Waiting for questions. All right, here's what I'm going to do. I'm taking a chance. I don't know what you can see now. Oh, there I am. You can see me. It's about 3. I'm looking at the clock on my laptop. 3:22. I'm sitting here in the science office. Rid just said, "Can you teach us something that will help us in the exam?" So that means I have to actually think about what's on the exam. I haven't done that for a few days. Hybridization. Let's talk hybridization. So I'm going to go back to sharing my screen now. See if it'll work. I'm kind of going slow here because I'm going to ask Rid to tell me if you can see my screen again. We had problems with screen sharing earlier. I think it worked this time still. We're looking at hybridization. I think this is something that might help you on your exam. 3 kinds of hybridization that we are expected to know: SP, SP2, and SP3. SP hybridization will generally be for AX2 it might be a situation where we have AX1E1, and an example of that would be the nitrogen. Oh, sorry. I hit that start key again. Okay, thanks, Red, for letting me know. This carbon, or this nitrogen, is AX1E1. It has a lone pair and it has a triple bond to the carbon. This carbon is AX2. So, and I'll talk about these again later. For sp hybridization, I have an s orbital and I have 3 p orbitals. And they are hybridized to form 2 sp orbitals. Gosh, okay, I'm going to erase some stuff here because I want to do this a little bit better. I have an s orbital and I have 3 p orbitals. And if I'm going to have sp hybridization, I'm going to have 2 sp orbitals left that are hybridized, and I'm going to have 2 p orbitals that are unhybridized. 4 orbitals here, 4 orbitals here. These are the hybrid orbitals. So for these hybrid orbitals, if this is the carbon, this is an sp orbital and this is an sp orbital, it's going to bond with the s orbital of the hydrogen. And if this is nitrogen, it's got an sp orbital and an sp orbital. This sp orbital is going to have a lone pair in it. This is going to be a sigma bond. So now I have to try, and you know that my artistic skills are not very well developed. I have an unhybridized p orbital here and an unhybridized p orbital here. That's going to make a pi bond. Using a different color, I have an unhybridized p orbital there and an unhybridized p orbital there. That's going to make another pi bond. And that's going to make the total of those 3 bonds. That's the triple bond that is in that nitrile. This is a nitrile. Nice little review of an organic concept or organic name. Sorry, I'm trying to bring my screen back. There we go. Okay, so that's sp hybridization. sp2 is going to combine 1 s orbital, and I have 3 p orbitals. And if I'm going to make sp2 hybridization, I will have 3 sp2 orbitals, and I'll have 1 p orbital that's unhybridized. This might be something like ethene. 120-degree bond angles. And these sp2 orbitals, I didn't draw that very well. Let me try again. I've got a carbon, and I drew a nitrogen. I've got a carbon with an sp2 orbital. I have another carbon with an sp2 orbital that's going to make the sigma bond. I have an sp2 orbital here to a hydrogen. I have an sp2 orbital here to a hydrogen. So the same thing's going to take place here, an sp orbital to a hydrogen, an sp orbital to a hydrogen. The hydrogen is going to be an s orbital. I also have 1 unhybridized p orbital, and that's going to make the pi bond. Now, if I have sp3, I'm going to take an s orbital and 3 p orbitals. I'm going to make 4 sp3 orbitals. And this might be something like CH4, methane. Bond angles are 109.5. And I have, I'm not a very good artist, but this is tetrahedral arrangement. And all 4 orbitals are equal energy. And that's kind of what hybridization is about. The hybridized orbitals all have equal energy, even though the orbitals that got sort of mushed together to make the hybrid orbitals don't necessarily have equal energy. So I think that my explanation maybe could have a little bit more detail that's included in the videos and or the PowerPoints on hybridization, but that's something that could help. So if my clock says 3:30, we started a few minutes late due to some technical difficulties. So I will say, here's what I'm going to do. I'm going to say last call for questions. I'll give you the teacher pause of, I know there's a little bit of a delay between when you hear me and when I can actually see a question from you on Twitter or through Rid's chat with me. So I'm going to pause for a second. And I'm going to see if you have any last questions. You certainly can email me with questions tonight when I'm marking labs. As long as I'm awake, I'll answer it. You certainly can email me later this week. And then we can decide. You can tell me next week, earlier in the week, if this was worthwhile. And actually having a screen that I can write on. I don't think last time I had much of a screen that I could write on. You can tell me if we want to do it again Wednesday evening before the test. Your test is on Thursday. I'm just kind of talking to waste a little bit of time here. I will say that you should enjoy the rest of your weekend. Keep it minty fresh. Blocks 2 and 4. I will get to see you on Monday. I'm putting together PowerPoints for you that have review questions based on what you requested from the Google form, the exit ticket. Block 7, we handled that on Friday. Tons of resources for you on Haiku. I think with that, I'll say thanks. Get some good studying in. And let me know if I can answer any questions. I can post this PowerPoint as well. I think that the video, I'm going to move this up now. I think you can see me. The video, I think, is saved on, if somebody can share that link on the Facebook group, I'll try and share it on Haiku as well. Have a good day.